Today we will be having a we will be continuing with what we were doing last time, and that is essentially saying different kinds of line drawing algorithms. Now, yesterday I had introduced this Bresenen's algorithm, and we had said that if we have to draw a line between a point 1 and a point 2, then the exact straight line between the two can be referred to as the true line. Okay. But in a raster refresh display, the true line will never be displayed. What would be displayed would be a set of pixels, which in this particular case might be pixels chosen something like this. And so on. So this set of pixels that are displayed, we'll refer to these as a displayed line. And this Bresenen's line drawing algorithm works on minimizing the error between the true line and the displayed line. And the error between the two is defined as the gap between the two. So if this particular pixel is being displayed, this pixel is actually, let's say, at the center of the center here. Okay, and the line is at the corner is at this, is supposed to pass through this point. So the error is this error E. Okay, so we will go through this algorithm. The basic principle is that we have to minimize the error between the true line and the displayed line. If we have a set of pixels like this, this is the true line. Okay. One pixel that has been displayed is this pixel that I have shown here in dark. Okay, you see, already seen the previous line drawing algorithm. We display pixels in a, let's say, in a loop. The first pixel is this one. Let's say the second pixel that is displayed is this pixel. Okay, so this is the first pixel. This is the second pixel to be displayed. We'll number them. Okay, so if initially pixel number 1 is displayed and then the pixel number 2 is displayed, we'll just see how the error would be defined in the two cases. If we look at this point, this pixel will actually correspond to the pixel something like this. Okay. The center of this pixel here will be at this level. So the gap between the two, let's say this term, this much, which is the error initially. Okay. At this point, the center for this pixel is at this level, and the actual line is through this point. Okay, so the error here is this error E. Okay, so initially this is the error, finally this is the error. So what we say is, as we move from this pixel to this pixel, the error is changing by this magnitude to this magnitude. And how much will be the difference in the two errors? The difference between these two errors will be equal to the slope of the line, because the line has moved up by this much. Initially line is here, then the line is here, so the line has moved up by this amount, and this amount would be equal to the slope of the line. Okay, slope of the line multiplied by unit pixel distance. Is that okay? So we'll say that as we move from one pixel to the second pixel, the error term E would change by an amount equal to dy by dx. Yeah, what's that?
So wouldn't we define the pixel to be as a square or something?
Okay, we had covered it earlier. If this is the array of pixels, if you are addressing this particular pixel, it's actually this pixel. Okay, you are addressing it at this location. So if let's say, for the sake of argument, I treat this as 0 0. I already said normally we treat the top left as 0 0. So if this is my origin, when I refer to a pixel 0 0, I am actually referring to this pixel. And referring to pixel 1 1, I am referring to pixel which is this one. Okay, so we are actually referring to a pixel as a square entity, and we are addressing it by the corner.
And the center is the center of the square.
And the center is the center of the square.
And when you write point 2,
this point 2.
Yes, sir.
Yeah.
So where does it lie on the square?
Where does it lie on the square?
The next square.
This is the corner of the pixel.
It will be the next square.
Yeah, so this actually would be a pixel like this.
So the center is the center of this square.
Yeah, actually the pixel is at the center, but we are looking at the line at the beginning of that pixel. Okay, the position of the line at the beginning of that pixel. Okay. So as we move from one pixel to the second pixel in this orientation, okay, the error term would change by an amount equal to dy by dx. Is that okay? But is another way in which the pixels can be displayed. I right now assume that this was the first pixel, the second pixel was this one. There is no reason for that to be true. The second pixel can actually be this pixel. Okay, we'll just see what happens in that case. The first pixel that is displayed is the pixel number 1, which is like this. And the next pixel that we decide to display is this pixel number 4, okay, which is okay. At this point, my error term will be this much. At this point, my error term would be this much. Okay, and by how much has my error term changed as I have moved one pixel in the x direction? Let's say E will be equal to E plus my line has moved up by an amount equal to this amount is dy by dx. Okay, so this line has moved up by an amount equal to dy by dx. And if you look at this pixel, earlier it was this pixel, now this pixel, the pixel being displayed is this one. So the pixel to be displayed has also moved up by an amount of 1 unit. Okay, so the error term, because of the line moving up, would increase by an amount of dy by dx, and since the pixel being displayed has also shifted up, the error term will come down by 1. Is that okay? So if the next pixel to be displayed is a diagonal pixel like this, then the error term would change in this manner. Is that alright? Now, right now we have not considered the case when the first pixel displayed is this one, and the second pixel to be displayed is then pixel number 3. That can also happen. Okay, we are not taking that into account, because what we will say right now is that this line has got a greater inclination toward the x-axis. Okay, so this line has a maximum movement in x direction, or the direction of maximum motion is the x direction. Okay, or the slope of this line is less than 45 degrees. Okay, if you consider octants like this particular case is for the first octant. Okay, and in the first octant, my direction of maximum motion is the x direction, and the error that I am measuring is in a direction perpendicular to that. Okay, so this error term is being measured in the y direction. Okay, so the line of maximum moment is the x direction, and error is measured in direction perpendicular to, let's say, the line of maximum motion, okay, or direction of maximum motion. Okay, so the error is measured in the direction perpendicular to the direction of maximum motion. Okay, is this all right? Okay, so now we have a scenario in which this particular pixel has already been displayed. Okay, the error here is this amount E. This is already displayed. Now I have to decide whether the next pixel should be this one or this one. What should be the criteria for deciding that?
The one which gives a lower error.
The one which gives a lower error. Okay. If this is displayed, the error will be E plus dy by dx. If this is displayed, the error will be E plus dy by dx minus 1. Okay, and we can compare the magnitude of the two errors and find out which is lower. Alternatively, at the previous level, whichever pixel was displayed, okay, whether this one or this one, I could have computed the error at the end of the line. Okay, and if this line is passing below this midpoint, okay, then I will display this pixel. If it is passing above the midpoint, like let's say somewhere from here, then I will display this point. Okay, so if this true line is passing above the midpoint, okay, then this pixel will give a lower error compared to this pixel. Okay, now I am looking at one step before. I am not looking at these two pixels, I am looking at these two pixels. Okay, if the line is passing exactly through the center, how much is the error?
0.
The error is 0. If the line is passing below that, okay, then how much is the error?
whatever amount it is passing.
Positive or negative?
Negative.
The error will be negative. If the line is above that, the error is positive. Okay. So if my line is above this, I will display this pixel. If my line is below this, I will display this pixel. Okay. Or in other words, we will say that if E is greater than 0, then we will display the upper pixel. Okay. So let's say this is number 2 and this is number 3. If E is greater than 0, then pixel number 3. And if E is less than 0, then pixel number 2. Okay. So what we'll basically do is we'll find out the error at this line. If the error is positive, we'll display this pixel. If the error is negative, we'll display the lower pixel. Again, depending on which pixel is being displayed, the error at the next term will be computed either according to this or according to this. Okay. If I am considering these two, the previous pixel has to be this one. Okay. Pixel number 1 has been displayed. If at the end of that pixel the error is positive, then we will display the pixel number 3. If at the end of that the error is negative, I will display pixel number 2. If pixel number 2 is being displayed, my error will be computed according to this formula. This is for pixel number 2. If pixel number 3 is being displayed, I will use this formula. Okay. So according to this method, we will write down the Bresenham's algorithm. Again, we are taking the case where this is the screen and we have to draw a line from a point 1 to a point 2. Okay. The point 1, let's say, is x1 y1 and the point 2 is, let's say, x2 y2. Okay. The first point that we display, that will be the pixel xy, which will be initialized to x1 y1. So at the start of the algorithm, we will compute the error term, which initially when we display the pixel xy, that is the starting pixel. Okay. Xy is the starting pixel that is being displayed. At the end of this pixel, how much is the error term? The line has moved up by an amount of dy by dx. Okay, and the center of this pixel is at 0.5. So at this location, the error will be dy by dx minus 0.5. Okay, this amount of the error that I have shown in this part of the figure is dy by dx minus 0.5. Is that okay? So the initial error that will be there at the end of the first pixel will be dy by dx minus 0.5. So when I have to decide, I will draw the figure clearly here. This is the initial error at the end of this pixel. So at this level, at this position, I have to decide whether this is my pixel number 1, whether the pixel number 2 is to be displayed or the pixel number 3 is to be displayed. In order to decide that, I will look at whether this E is positive or negative. If this E is positive, I will display this. If E is negative, I will display this. Okay. So accordingly, we will write the algorithm. We initialize E, that is error term, to be dy by dx minus 0.5, and then we have a loop Okay. So we have initialized the error term to be delta y by delta x minus 0.5, and this, as I said, would be the error term or would be the error at the end of the first pixel, that is at this location. Then we are repeating this part in a loop. We'll first plot the first pixel. Okay, we'll plot the pixel xy. Then we'll say if E is greater than 0. If E is greater than 0, then the next pixel to be displayed is the pixel number 3. If pixel number 1 is xy, pixel number 3 is x plus 1, y plus 1. And pixel number 2 would be x plus 1 and y. Okay, so we have plotted the first pixel xy. If E is greater than 0, then we are saying y is equal to y plus 1 and E is equal to E minus 1. Okay, that means we are changing the value of y to y plus 1. Okay, and the error term E we are saying will be equal to E minus 1. And then immediately out of this if statement we are saying x is equal to x plus 1. Okay, so x is also being made x plus 1 and error term is being changed to E is equal to E plus delta y by delta x. We have already said E is equal to E minus 1, and after that we are saying E is equal to E plus dy by dx. So effectively E will be equal to E plus dy by dx minus 1. Okay, so if my error term is greater than 0, then we are changing x to x plus 1 and y to y plus 1 and E to E plus dy by dx minus 1. Okay, so if the error is positive, y is becoming y plus 1, x is becoming x plus 1 and E is becoming E plus dy by dx minus 1, which is effectively what we want to do if the pixel number 3 is to be displayed. Okay, if the pixel or if the error term is less than 0, in that case, if E is less than 0, these two steps will not be done. We'll just say x is equal to x plus 1 and E will be equal to E plus dy by dx. which is what we want to do for pixel number 2. X will change to x plus 1 and y will remain as y and e will change to e plus dy by dx. Okay, so effectively if e is less than 0 then pixel 2, if e is greater than 0 then pixel 3. Okay, and mind you, all this we are doing when our line is in the first octant in this part. Okay, if we have to draw a line from x1 y1 to x2 y2, when we say that the line is in the first octant, we are saying y2 is greater than y1, x2 is greater than x1 and x2 minus x1 is greater than y2 minus y1. So this algorithm that we have written right now is for the condition when these conditions are satisfied. Okay. If our line is in some other quadrant, instead of the line being here, if our line is to be drawn in this octant, okay, if we have to draw a line starting from this point with a slope like this, then the direction of maximum motion is the y direction. Okay, if the direction of maximum motion is the y direction, then my algorithm will change accordingly. Okay, what will be the changes?
Interchange x and y.
Again?
Interchange x and y.
We'll essentially interchange x and y. Okay, so we'll have to rewrite the algorithm with x and y interchanged. Similarly, we'll have to make similar changes if my line is like this or in any other octant. Okay, so the algorithm the way I have written right now is only for drawing lines in the first octant. And in this, delta y is nothing but y2 minus y1. Delta x is nothing but x2 minus x1. Okay, and of course e is the error term, x and y are the coordinates of the current pixel being displayed. Of all these, x1, x2, y1, y2, they have to be integers, because we are talking of drawing a line from one pixel to a second pixel. Pixels will always be addressed by integers. So x1, x2, y1, y2, they are all integers. Therefore delta x and delta y, they are also integers. Okay, x and y will also be integers. Okay, the only thing that is not an integer here is this error term e. Okay, e has to be a real number. Okay, similarly, all these are the places where e is being used. E has to be a real number because we are dividing two integers and we have a real number 0.5 coming in the picture. So e has to be a real number. And if you notice in this complete algorithm, e is important only for finding out the sign of e. We are only bothered about whether e is positive or whether e is negative. Okay, we are not bothered about the actual magnitude of e. Since we are not bothered about the actual magnitude of e, we will say that instead of coding the algorithm on the basis of e, we will code it in terms of e multiplied by delta x multiplied by 2. Okay, what I mean is, if I take this statement and multiply it by 2 times delta x. If I multiply it by 2 times delta x, my statement will become e will be equal to delta y times 2 minus delta x, sorry. Okay, now my error term E is not the error term which we had shown in the figure earlier, but it is that error term multiplied by 2 times delta x. Okay, so error is equal to, or E is equal to delta y times 2 minus delta x. The other places where I am changing E are this line and this line. These statements also I will multiply it by the same amount, 2 times delta x. So this statement will become E will be equal to E minus 2 times delta x, and this statement will become E will be equal to E plus 2 times delta y. Okay. If I make these changes, my program will still be valid. Okay, because I am only bothered about the sign of E. So wherever I am using E, I have multiplied by a constant amount. Okay, so the sign of E will still remain the same. Okay, mind you, delta x is a positive number. Okay, because in this case I have taken x2 to be greater than x1. Okay, so delta x is a positive number. So I multiplied my term E by a positive number, by a positive constant. Okay, so the sign would remain the same throughout. Okay, which effectively means this statement will be replaced with this one, this will be replaced with this one, and this statement will be replaced with this one.
E is also an integer.
Pardon?
E will also be an integer.
Now E will also become an integer. Okay, the reason why I am doing this is after this all my variables will become integers. Okay, I will not deal with any real numbers, and in addition to that I will not have any division in my algorithm. There will be no integers and no divisions. Okay, which means the algorithm can be very easily implemented on hardware and the algorithm will be very fast. Okay, because integer numbers will take less memory, and integer addition and multiplication are easier to carry out. There are no divisions involved in it. Okay, and this version of the algorithm is referred to as integer Bresenham algorithm. Integer Bresenham algorithm. Okay, or the integer version of the Bresenham algorithm. Okay, any question on the integer version of the Bresenham algorithm? Okay, this algorithm is superior to the previous algorithms primarily because we are dealing only with integers and we don't have any division in the algorithm. If you don't have divisions, the competition is faster. Okay, divisions are very expensive. Okay, so this is the integer version of the Bresenham algorithm. Now, the next thing that we will take up is how to draw curves, or to start with drawing of circles. Okay. For drawing circles, we will again use what is referred to as a DDA algorithm, digital differential analyzer based algorithm. Okay. In this DDA algorithm, when we are drawing a straight line, we had said that the slope was equal to a constant which was y2 minus y1 divided by x2 minus x1. Okay. If we have to draw a circle, then let us say this is the origin which is 0 0. At any point xy, what is the slope? For a circle, how much is dy by dx? It will be minus x by y. Okay, you can verify it very easily. You know the equation of a circle is x squared plus y squared is equal to r square. The circle is passing through the origin. Differentiated with respect to x, you will get 2x plus 2y times dy by dx will be equal to 0. And this will give us this. Dy by dx will be equal to minus x by y. Okay. So we will basically be using this fact that dy by dx will be minus x by y. If you remember the line drawing DD algorithm, we had said that if xy is a pixel that has been drawn at a particular stage, the next pixel to be drawn will be x plus epsilon times delta x, comma y plus epsilon times delta y. Okay, so this increment was proportional to dy by dx. Okay, we will do the same thing now. We will say that from xy, the next pixel to be drawn will be by an increment proportional to this dy by dx. Okay, so if you are taking increment proportional to this dy by dx, my x will change to x minus epsilon times, plus epsilon times y, and y will become y minus epsilon times x. Okay, but dy by dx is equal to minus x by y. Okay, my increment in the y direction is minus epsilon x, my increment in the x direction is epsilon y. So the ratio is minus x by y. Okay, so we are taking an increment in both x and y by very small amounts. Okay, and so that the next pixel to be drawn will be in the direction of the tangent, will be in the direction of the slope at that point. Okay, so if you just look at this figure, this is a pixel xy. Okay, we are talking in this is the initial pixel being drawn. The next pixel to be drawn is along the slope of the curve, the slope of the circle at that point. So that will be a pixel, let's say somewhere on this tangent at a point like this. Okay, so if I call this pixel, this particular pixel as xn yn, and the next pixel to be displayed as xn plus 1 yn plus 1, I can write xn plus 1 will be equal to xn plus epsilon times yn. Okay, and yn plus 1 will be equal to yn minus epsilon times xn.
So if we want to draw n plus 2, then xn plus 1, yn plus 1, the slope at that point will not be defined because it is not lying on the surface.
I'm just coming to that. Okay. Now, if xn yn is a particular pixel that has been drawn, the next pixel to be drawn we are giving by xn plus 1 yn plus 1, or I can write it in the form of matrix xn plus 1 yn plus 1 is equal to xn yn multiplied by, what will it be, xn and yn, so 1 epsilon minus epsilon 1. Is that okay? Is that okay? Thanks. So xn plus 1 yn plus 1 can be found out by this system of linear equations. Is that alright? Now if I keep applying this relation consecutively, this is the first pixel that has been drawn, next pixel is this. The next pixel to be drawn would again be found out by the same relation. So my xn plus 1 yn plus 1 will become xn yn, okay, and then from this point I'll take a tangent like this and I'll continue in that process, okay. But effectively what is happening is this point xn plus 1 yn plus 1 is slightly further off from the center than the point xn yn. It is not exactly at the same radius, okay. The difference will be very small, but there will be a difference. This distance would be r, and how much would this distance be? We can find out from here, okay. If we take if you want to find out the magnitude of or the radius of this point xn plus 1 yn plus 1, we will get xn plus 1 squared plus yn plus 1 squared will be equal to xn square plus yn square multiplied by 1 plus epsilon square. That is the magnitude of this determinant. Okay. So the distance of this point xn plus 1 yn plus 1 from the origin will be, if this distance is r, it will be r multiplied by under root of 1 plus epsilon square, okay, or the new r would be small r multiplied by 1 plus epsilon square, even though epsilon will be a very small number, okay. But even then, as we keep repeating this process throughout the circle, by the time I come back here, I will not close here, but I will close slightly further off, okay. Some error will creep in because the same process is being repeated throughout, okay. So effectively we will get a spiral and not a circle, okay, because the radius will keep increasing by an amount of 1 plus square root of 1 plus epsilon square, or by a factor of under root of 1 plus epsilon square every time, okay. To avoid that, instead of using this relationship or this system of equations, what we will do is instead of using it this way, we will make a small change. Instead of xn, we will make it xn plus 1. Okay, and if we represent this in a similar matrix notation like last time, we will get Okay, you can verify the relationships. Okay, essentially instead of xn plus 1, we put in this expression and then again rewrite it in the matrix form. Okay. Now if I look at the radius at this point, I will get this multiplied by the value of this determinant. What is the value of this determinant? 1 into 1 minus epsilon squared minus this, which is 1. Okay, so the radius here, that is Rn plus 1, will be equal to the radius at Rn. Okay, so just by making this small change, we will be able to get a circle accurately. Okay, so the next point, instead of being here, will be at the circle boundary, and the circle, instead of becoming a spiral and ending here, will end at this location. Okay, so this is how we can draw a circle using a DD algorithm. Okay, if we want to draw any other curve, if we know the equation of the curve, we can again find out the slope. Okay, for any curve, if we know the value of dy by dx, then we can draw that curve by taking increments proportional to dy and proportional to dx. Okay, let's say if I know that dy by dx is equal to minus x squared, just for the sake of argument. Okay, then I will give an increment in the y direction which will be proportional to x square. Okay, and we can continue that way.
What will be epsilon proportionality constant?
Okay, now in the case of drawing a circle, I am multiplying epsilon by yn. Here I am multiplying epsilon by xn plus 1. Magnitude of both yn and xn will be in the range of minus r to plus r. Okay, if you are drawing the circle, xn and yn will always vary from minus r to plus r. So epsilon times xn or epsilon times x should be just less than 1 pixel. That is the initial criteria, right? If it is very much less than 1 pixel, then we do wasteful computation. If it is more than 1 pixel, then we don't draw all the pixels. Okay, so epsilon x should be just less than 1 pixel. So again, one criteria we can use is, we'll take epsilon to be equal to 1 over 2 to the power n, such that 2 to the power n will just be greater than r. Okay, if 2 to the power n is just greater than r, and r should be greater than 2 to the power n minus 1. Okay, so let's say if the radius is 50, then our n will be 6, epsilon will be 2 to the power minus 6. So if you are drawing a circle with a radius of 50 pixels, then epsilon is 1 by 64. Okay, so every time we give an increment, that increment will be of 50 by 64 or minus 50 by 64. That's the maximum increment we will be giving.
Why can't we put epsilon straight away 50?
Because then at this point, okay, in the y direction, my increment will become 1 pixel. Okay, it won't be, and in the x direction, of course, at this point the increment would be 0. So here the pixel in the, here the increment in the y direction will be 1 complete pixel. We might not want that.
We will have to do that if that is the case. Sometimes the circle, at the end of the circle you get a straight line, sort of 4 quadrants.
Even in this case we would. Okay, even in this case you would get that. Okay, because I don't know whether I have figured for that. Probably no. Anyway, the pixel that will be displayed will look like this. I mean, a few straight, then here, like this. At the end, they'll always almost look vertical.
So
Yeah.
does it also have something to do with the division by power 2 will be easier?
Division by the power of 2 being easier.
Yes, sir.
That is 1, because I'm dividing by 2 every time. Okay, so if you have any number, dividing it by 2 means 6 right shifts. I mean, in this case, 6 right shifts or n right shifts. Okay, but as if you want to divide it by 50 every time, at this point, the value of x and y is, let's say, 30 and 30. Okay, you have to divide 30 and 30 by 50. Okay, which is going to take more time than just doing n right shifts. Okay, so that would be there. Okay, so for finding out the value of epsilon, this is one way of doing it. The algorithm will work equally well if you just take a random value of epsilon, as you're saying 1 by 50 or something like that. Okay, you'll still get a circle. The algorithm would work.
So what would happen if epsilon x is equal to 0.5?
Epsilon into x, it can become 0.5.
So which pixel would we would we choose the pixel or next pixel, or would we still remain on the same?
Okay, we are rounding it off. Okay, if you remember in the DDA algorithm earlier, we are rounding off whatever value we were computing. So whatever value we for xn plus 1 and yn plus 1 we get, we will round off that value. If you want to change it to truncation, we'll have to add 0.5 every time and so on. We'll add 0.5 once in the beginning and take care of that. But nevertheless, the effect is of rounding it out. So if we xn plus 1 comes out to be 50.5, we'll take it to be 51. Okay, any other question on this? Okay, in that case, I think we'll end today. We'll end here today, and in the next class, maybe we'll go into some other algorithms for display purposes, specifically algorithms with respect to maybe clipping and windowing and transformation and so on. Okay, that's all.